Hello everyone, welcome to CCNA Audionotes on the channel Ashwarma C5IT. And continuing with our syllabus, in this video, we are going to talk about protocols in general and then take a look over the most influential protocol over the last 25 years, that is OSPF, along with EIGRP. These both protocols are the primary IPv4 routing protocol. But first, what is a routing protocol? From last couple of videos, we are talking that IP, which is internet protocols, come in two version, IPv4, IPv6. If those are not routing, then what else is? The main source of confusion is that people often don't able to differ between a routing protocol and a routed protocol. The routing protocol refers to the algorithm that a router uses to learn, advertise, select, or react to the changes in network, while routed protocol is a form of packet structure that is considered a standard when we talk about network communication between different devices. The IPv4 or IPv6 are the routed protocols because it shapes the packet, what information does it contain, and how the other device will extract the information after it has been encapsulated. Our second last episode was of the routed protocol, in which we discussed how IPv4 and IPv6 addressing works. But still, there's a lot to discuss, like what are the contents of their header length, and different values that we have to remember in order to excel CCNA exam. Don't worry, we are going to do that also. This video is about the routing protocol, OSPF particularly. When we talk about routing protocol, we get confronted with a term called autonomous system. An autonomous system is a network under the administrative control of a single organization. The simple example is the network inside of your college campus, which is solely maintained by your college IT department. And just like IP address, autonomous system can be registered as well with IANA, that is Internet Assigned Number Authority, and the number assigned to it is called ASN, which means Autonomous System Number. Continuing with the example of college LAN, there is a higher possibility of having multiple routers, and it will be a tough task to manually configure all the router and update them accordingly. So what we use is the interior routing protocol. Having an interior routing protocol automates the basic route management on a router. But when it comes to connecting with routers outside of college campus, that is external network, we use exterior routing protocol. So in conclusion, that the routing protocol come in two versions, an interior routing and an exterior routing. And depending on what an interior routing protocol pivots its routing decision, it is further divided into three types. First type is distance vector protocol. Second is link state protocol, while the third is hybrid protocol. Starting the discussion with distance vector protocol, RIP and IGRP are the most famous one. RIP stands for Routing Information Protocol, while IGRP stands for Interior Gateway Routing Protocol. As the name suggests, they use the distance as their pivot point or metric to decide which path to select. In terms of networking, the distance is known as the hop or the connection of point between two routers. For example, if three routers, that is router A, B, and C, are connected in series, the distance between A to B is 1, while distance between A to C is 2, because it has to cross two hops. One more thing that I want to add is that RIP, Routing Information Protocol, comes in three variants. First is RIP itself, then RIP version 2, and finally the RIP NG. NG stands for next generation. Now let's talk about the link state protocols. Again, the name is self-explanatory that this kind of protocol uses the status of link like its speed, uptime, reliability factors to determine whether to use this or that link. Two examples of this protocol are OSPF and ISIS. OSPF stands for Open Shortest Path First, while ISIS stands for Intermediate System to Intermediate System. And finally, the Hybrid Interior Routing Protocol, which is exclusively designed by Cisco and assimilated by Networking World as one of the best protocol for for interior routing, as it is the best of both worlds. The protocol is EIGRP, which stands for Enhanced Interior Gateway Routing Protocol. The decision making matrix of EIGRP is quite complex, but in short, it considers bandwidth of the link, load on the link, delay, reliability, and maximum transmission unit to compute the best path for the job. So, we have talked about the most famous ones, interior routing protocol, but let's not forget the exterior routing protocol as well. There is only one of it, that is BGP, which stands for Border Gateway Protocol. Border Gateway Protocol uses the best path algorithm to decide which best path is to install in the IP routing table. By best path algorithm, BGP assigns the first valid path as the current best path, and then it goes comparing this best path with the next path available until the end of the list. It uses multiple different metrics, weighting systems to ultimately determine the best path. As this is not in our syllabus, we are not going in it for further details. But what is in our syllabus is OSPF. So get ready to get down in the OSPF rabbit hole. The OSPF process starts on a router by issuing the command IP OSPF followed by a process ID. The PID stands for process ID, is locally significant and is used to modify or terminate the OSPF process and need not to be same in all the communicating routers. In order to broadcast the routing information, OSPF first establish a neighbor relationship with the other router. It does so by greeting the other neighbor with hello messages. Hello messages are type 89 IP messages that is multicasted over 224.0.0.5, and in case of IPv6 it is multicasted on FF02 double colon 5. Every other router that need to form an adjacency or a neighbor relationship have to listen and respond to this multicast. Essentially, the OSPF hello messages are the sharing of router ID, which is a 32-bit field serving as each router's unique name or identifier. Router ID can be manually set, configured, and if not configured, the OSPF process will pick the highest loopback interface address as its router ID. And if there is no loopback address configured on the router, then it will pick the highest physical address as its router ID. Being a OSPF neighbor and sharing all its database is a 7-step process which only be completed successfully if both the router that we want to become neighbor fulfills the following criteria. The interfaces on the router must be in up state and no filtering must be applied on the protocol messages. The router's interface must be in the same subnet and they must be properly authenticated to communicate. Their hello and dead timer must be matched By default, hello timer is of 10 seconds and a dead timer is of 4 times of hello timer, that is 40 seconds. Their router IDs their router IDs must be unique. Their process must be running properly and they are in the same area. An OSPF area is the logical connection of contagious network and router that have the same identification. All the requirements that I have discussed until, along with having the same MTU and OSPF network type, are followed, then the two routers are said to be in the same area. And after that, the exchange state starts. It all starts with down state when two router don't know each other. In most human possible way, we can understand it as arranged marriage or dating of router. Then one of the router multicasts its first hello packet and we are in a state 2, that is attempt or init state. Along with router ID, the hello packet also contains some additional configuration values such as area ID, hello interval, hold down timer, MTUs, and some other flag. In an multicast environment, this second stage is known as init stage, while in a point-to-point environment, where the router have to use unicast messages to send hello, this stage is known as attempt state. If the configuration values matched, the other router will add the first router in its routing table, in its neighbor table, and reply it with its hello packet. Now attention has to be paid on the term that now the second router knows the exact address of first router. It will unicast its reply, and beside the configuration values, the second router also sends it neighbor table data, which is which will also contain the first router entry. So this will double checks and assures that this second router has accepted the first router neighborship request. Just within 3 steps, the neighborship relation established, and it will be as long as the router continues to send hello messages. But if the gap between hello messages exceeds the dead interval, that is 4 times of hello, both router will go in down states and the process have to be restarted. But before we understand how routers will exchange routing information, we need to understand the types of network, as OSPF use different types of exchange process for different types of network. The three kinds of network are point to point network, broadcast network, and finally non broadcast multi access network. Point to point networks are the connection between a single pair of router in which both routers know each other very well. So they form their full adjacencies is the synonym for the process of sharing each other's routing table. The hello packets are sent using the multicast address 224.0.0.5 and no designated router or backup designated router election take place. The term designated router and backup designated router will be explained in next few steps. But first finish the network. Second is broadcast network type. The network that are able to connect more than two devices at once are broadcast network. For example, Ethernet and FDDI. FDDI stands for Fiber Distributed Data Interface, which casually be understood as local area network on steroids, as it uses fiber optic cables and can extend up to range of 200 kilometers. So in this kind of network, all router form adjacencies with only designated router and backup designated router. So there is a requirement of making elections for designated router and backup designated router, which I'll be referring from now as DR and BD. DR. A designated router is a superior router with the responsibility of forming adjacencies with every other router in its area. The reason behind electing a designated router DR is to utilize the bandwidth in an efficient way. If no DR is elected, every router tries to multicast its routing table, and then there will be no space left for the actual traffic. BDR is the same as DR but is waiting for the main DR to fail in order to take its place. Hence the name backup designated router. We will discuss its election in a bit, but now we have understood the purpose of a designated router as it requires to form adjacencies with every other router. Every other router uses the multicast address 224.0.0.6 to update the designated router, while the designated router uses a multicast address of 224.0.0.5 to update every other router. And finally, the NMBA network, that is non broadcast multi access network. These are also capable of connecting more than two devices, but they lack broadcast capability. The X25 and frame relay are the example of this kind of network. So without broadcast capability, the OSPF neighbor must have been defined manually and statically. So here all the OSPF packets are unicast and the election of designated router and backup designated router takes place. And there exists a variation of NMBA network, that is point to multi-point network. In this case, networks are configured as the collection of point-to-point links. Point to multi-point network also lacks broadcasting capabilities, but it offers at least multicasting. So once the network is configured statically, the OSPF packets can be multicasted, and still there is no need for election of designated router and backup designated router. So, in conclusion, non broadcast multi access have two network types, one that need BR and BDR election, while the other with point to point, while other with point to point and multi point link, which do not need DR and BDR elections. Finally, we have come to a point where we are going to discuss how the DR and BDR election take place. The main deciding factor is the router priority, which is a manually configured value varying from range of 0 to 255. The default priority value is 1, and if we set it to 0, the router will never become a designated router. And if we set it to the highest 255, it will always become the designated router. And in case where the highest priority value match, the router will use the router ID to elect a designated router. Right after the formation of adjacencies, we move to next stage in the process, that is X start stage. Now in X start stage, and another form of relationship establishment takes place known as master slave relationship. Master slave relationship has limited purpose and is not to be confused with DR and BDR. This relationship is the rivalry between the interfaces of two neighboring routers for starting the exchange process. The router with higher router ID becomes the master and begins the exchange process. And once the master slave relationship settled, they will establish the initial sequence number which will be used in routing information exchange process, and this sequence number ensures that routers get the most accurate information. And after this, the master slave relationship has no meaning, it becomes worthless. After this, the exchange process begins. The master starts sending DBD, which stands for database description and is also referred as DDP, which can be expanded as database description packets. It contains the list of LSA. LSA means link state advertisement, and it is a list which include link state type, cost of link, identity of the advertising router, sequence number, etc. It is merely an index, not the full advertisement. When the slave router receives this DBD, which it compares with its own routing table, right after receiving of DBD, the slave router sends a LSACK, which is link state acknowledgement packet, back to the master router, assuring that it successfully received the description packet. And after receiving the database description, the slave router will compare it with their own LSDB, which stands for Link State Database. LSDB is the collection of all the LSA received by a router, along with its sequence number to keep an eye on. And when it finds something new in the description that it don't have in LSDB, it requests it from the master to send the complete advertisement with a request that is known as LSR, which stands for Link State Request. And right after the request is made, we proceed to another state, that is loading state. In this state, the actual transmission of data takes place, as after receiving LSR, the master router will fulfill its request by sending it complete advertisement. This process happens and continues until the both router have the same LSDB. And yes, the router maintains a separate LSDB for each area. And after that, we proceed to next state, which is full state, an assurance that both have identical LSDB, and the only task remaining is to maintain adjacency. Every LSA has a default lifetime of 30 minutes. Even if it is unchanged, it must be reflooded in every 30 minutes to maintain network trust. I have countless time mentioned the designated router and the backup designated router, but by what term we associate the other routers in the network, which is neither DR nor BDR. We call them DR other, all written in capitals, DROTHER. It feels like that we have studied a lot about OSPF, but last few terms are still remaining. Those are the special names for some specific areas and the link state advertisement types. Starting with the terms related specific area, we have ABR, that is area border router. An ABR is an OSPF router with its interface connected to the backbone area to at least one other area. The backbone area is a special term given to other router from which we initially scaled the network, and any other router that connects to this backbone area we term as backbone router. And it is a naming convention that we mention the backbone area as area 0. It's not a strict rule that it cannot be named something else. When we route to a subnet inside the same area as the router, we called this route as intra-area route, while a route to the subnet in an area which is the router is not a part of, we called that route as inter-area route. In basic terms, an inter-area route transverse the area. For example, area 1 is connected to area 4 or 5. That is an inter-area route. While when two routers communicate within a single area, for example, two routers in area 1, it the route will become intra-area route. Now there is also something called stub area and not so stub area. So the stub area is the area with a single point of connection to backbone area. This means that only free flowing traffic within a stubby area are intra area traffic, while every other traffic must have to pass from an area boundary router to maintain connection from outside the area itself. Not so stubby area is quite like this stubby area, but slight difference is that it is restricted by the protocol, means an area that connects to outside of world but not with help of OSPF. It can be understood as an stubby area but with an another protocol providing it route outside of the external area. So it does not have to depend on only OSPF as its default gateway to connect to external world. To get more information on stubby area and not so stubby area, please refer to my community section on YouTube to get a diagrammatic view. It is one of the overwhelming topic, but in actual, it is a very easy one to get. So don't miss to check community tab. And finally, before wrapping up, let's discuss about the three most common LSA types. The type 1 LSA is known as router LSA, which has the primary purpose to describe a router, its router ID, interface, IP address, its subnet mask, and finally its interface status. A type 2 LSA is known as network LSA, which describes a network that has a designated router. So it contains the information about designated router, backup designated router, their IP addresses, subnet ID, and finally their mask. And finally, the type 3 LSA is also known as summary LSA, which is a misleading name in my behalf as it contains the description of a subnet in another area along with its subnet ID, mask, router ID of the area boundary router, etc. There exist many more kind of LSA, but they are not in syllabus. And if you love the OSPF as much as I love it, make sure to watch a Kevin Wallace OSPF deep dive video to know about all the other information on different kinds of LSA. But before wrapping up the OSPF, some more bonus things that I want to discuss. We have already understood the significance of having a default route in the network. It enables every router to connect to the internet without bouncing the traffic, without bouncing the traffic between one another. So if we want to enable the default information sharing between OSPF neighbors, we have to pass default information originate command on the router having the specified static default route. Only then this router will flood a different kind of type 5 LSA to all the other routers to make sure an entry of default route in other router as well. But in case of a router without having a default static route, we have to modify the command slightly bit by adding keyword always in last. So the new command will be default information originate always, and by this the designated router, the router having default route, which is an ASBR, stands for autonomous system boundary router, will advertise a default route even if the originating router does not have one. The ASBR refers to the router that connects a router with outside world. And let's wrap this chapter up by understanding how OSPF calculates route. So the metric that OSPF use is known as cost, and cost depend on the bandwidth of the interface. However, we can manually change the cost on per interface basis using the command IPOSPF cost and the value of the cost that we want, or even altering the bandwidth setting of the interface also changes the cost value. It is because during automatic cost calculation, OSPF divides reference bandwidth by the actual bandwidth of interface. By default, the reference bandwidth is 100,000 kilobits per second. So before dividing the bandwidth to get cost, we have to first convert the link speed or link bandwidth in kbps and then dividing 100,000 with the link bandwidth, we get OSPF cost. For example, for normal Ethernet, that is 10 Mbps, which translate to 10,000 kbps. When we divide 100,000 kbps with 10,000 kbps, we get a cost of 10. While for fast Ethernet, that itself is of 100,000 kbps, when we divide the reference bandwidth, which is itself is 100,000, we get a cost of 1. However, in case of gigabit Ethernet, that translate to 1 million kbps, and after dividing the reference value with 1 million kbps, we get the result in decimal, that is zero point 0.1. However, OSPF does not take account of decimal values. So even for gigabit Ethernet and beyond, the OSPF cost will be 1. There is freedom to expand the reference cost to make the comparison more worthy using the command auto-cost reference-bandwidth with the speed in kbps. And in case where multiple paths have the same cost, the OSPF can offer some form of equal cost multipath balancing. By default, it supports up to 4 paths of load balancing. However, the maximum path depends on the router platform. And this is how we wrap up the OSPF. If you know something else or realize that I have missed something, please mention it in the comments. Thank you for your time and patience.